So this lesson is about equations of lines in the three-dimensional space. You are familiar with the equation of lines in the two-dimensional space. Here we talk about three-dimensional space. One way to explain this to obtain the formulas, before showing the formulas, is suppose we have a three-dimensional space coordinates like x, y, and z. And we have a point of the line, and instead of saying the slope, but in three-dimensional space, we say we have the direction of the line. So suppose this vector shows the direction of the line and passing through that point. So suppose this vector, say v, is a vector which shows the direction of the line passing through that point P. Obviously, be careful, all of these are in the three-dimensional space. Obviously, the line looks like parallel to that V, and passing through that point will be this line. So P is a given point, and V is the direction of the line, or direction vector. Okay, so I can look at every point on this line as a vector. So P itself is a vector. First of all, let me give coordinates to P. Suppose the coordinates of P are x0, y0, and z0. It's a point in the three-dimensional space. And I connect the origin to that point. So this becomes the vector x0, y0, z0. In the first week, we talked about this, that when we use this notation, it's a vector, not a point anymore. So to obtain any other points or any on this line, on the blue line, or in fact, any vector corresponding to that point. So let me pick one arbitrary point on that line. So like this point, or in fact, the corresponding vector is this vector. So if that point, as a point, this arbitrary point on the line is x, y, and z, this vector is the vector x, y, and z. So how can I obtain this vector x, y, z using the given vector? That's the vector connecting the origin to the point x0, y0, z0 in the direction of v. So in fact, this vector, which connects the given point to every point on the line, is parallel to v. So it is some multiple of v. So it's some real number t times v. V is the vector that you see here, this vector. So t times v is the vector which connects the given vector to any vector that its end point is on the line. In fact, this is in the vector equation of the line. So based on this explanation, the vector equation of this line is going to be the given point that I look at that as a vector plus t. T could be any real number. So as t changes, I get different points on the line times the direction vector of v. Suppose this direction vector of v, so this direction vector of v, suppose I give a name to, give coordinates to that, A, B, and C. So t times, or scalar multiplication with the vector A, B, C. So this gives me the vector equation of the line. Any point x, y, z that I look at that as a vector connecting the origin to the point x, y, z is equal to the initial vector plus t times the vector ABC. Let me give an example. Find the vector equation of a line in the three-dimensional space passing through this point 2, 1, -3, and with the vector direction of 5, 4, -6. So based on the formula that I just explained, it gives us that every vector on this line is this given vector plus t times the direction vector. Just one explanation. Usually this will be given as a point. So I should use in the problem, usually it's given as a point. But when I translate this as a vector, I write it this way. I use the vector notation, not parentheses anymore. So for simplicity, again, one more time, suppose I only show the origin of the three-dimensional space, and I have x and y, x, y, z, like x coming out of the screen, y and z. But for simplicity, let me ignore those. Just keep the origin of the coordinate system, the origin O. So if I have one point of the given line, x0, y0, z0, and the vector direction of the line, suppose the vector is parallel to, the line is parallel to this vector v, and vector v is consisting of three coordinates, a, b, and c. Then the line that passes through P and parallel to that vector V every point, if I look at every point as a vector, so the point P is going to be the vector x0, y0, z0. Every other point, this point here, it will be as a vector that vector x, y, z will be the initial vector x0, y0, z0 plus t times the direction vector a, b, c. Be careful that when t is positive, I get a point which is on this picture on the right side from the angle we are looking at this point. It will be on the right side of P. And if t is negative, it will be the other way. So here in this picture, the point that we found here corresponds to some positive t. That t is positive. But for another point, the other side of P, for example, a point like here, if I look at the and if the coordinates of that endpoint is x, y, z, or the corresponding vector is the vector x, y, z, again, it is the initial vector x0, y0, z0 plus t times a, b, c. This time that this t is negative. So t is less than 0. T equals 0, give me exactly point P, or the vector that connects the origin to the point P. Okay, so far we know that the vector equation of a line, a point x, y, z is on a line if it is of the form, or can be written of the form of some given vector x0, y0, z0 plus t times some position vector, which gives us the direction of the line. So this is the vector equation of a line. Vector equation of a line. Now let's do some algebra with the right side of this equation. So x, y, z equals x0, y0, z0. That t is a real number when multiplied by those three coefficients. In other words, we are doing the scalar multiplication. It's going to be TA, TB, and the TC. And now I can combine these two. The first coordinate added to the first coordinate, x0 plus TA, comma, y0 plus TB, comma, z0 plus TC. This is equal to x, y, z. So these two sides are equal. I can set the first equation equal to the first coordinate equal to the first coordinate. So the x coordinate is x0 plus TA. Y is y0 plus TB. And z is z0 plus TC. In an example, x0, y0, z0 are given, a, b, and c are given. But as t changes, we get three coordinates of a line in the three-dimensional space. This form of the equation that x, y, and z are given in terms of t, these are together, this is called the parametric equation of the line. Of the line. So let me give an example. How do we find the parametric equation and vector equation of a line? So for example, let 10, 2, and -3 be a point of a line, and the direction vector of the line is this vector, 4, 7, and -5. Part 1, find the vector equation of the line. This is something that we have already done before the parametric equation. So one point xyz that I showed as a vector. So the vector that connects the origin to any point xyz on the line is going to be the position of this point, the given point, as a vector, which is vector 10 to -3 plus t times the direction vector 4, 7, -5. So as t changes from -infinity to +infinity, I will get one straight line in the three-dimensional space. So in other words, the endpoints of these vectors x, y, z obtained by in this way, all of them, they form a line as t runs from -infinity to +infinity. So in part 2 of this problem, find the parametric equation of the same line. The parametric equation. So of the same line, I want to for the same line, I want to find the parametric equation. So I would suggest that you pause the video and try to do it on your own. And then you can watch the solution. So for the parametric equation, I need to find what is x, y, z in terms of t. Using the vector equation, I can see that x is 10 plus t times 4. So the first coordinate x is 10 plus t times 4, or it's better way to write that 4t. How about y? Y is 2 plus t times 7. So y is 2 plus 7t. And finally, z is the third coordinate minus 3 plus t times negative 5. So z is going to be negative 3 minus 5t. So as t changes, we get the three coordinates of the same line. Like, for example, suppose t is 1. When t is 1, x is 10 plus 4, 11, y is 2 plus 7, 9, and z is minus 3, minus 5, minus 8. So let me just repeat. I think I mentioned it in the wrong way. Let me repeat what I had according to the example I prepared. Suppose t is 1. So x is going to be 10 plus 4 times 1 is 14. And y is 2 plus 7 times 1, which is 9. And z is minus 3 minus 5 times 1, which is minus 8. So the point with three coordinates, 14, 9, and minus 8 is on that line. So if I give another value of t, I'll get another three coordinates. And those three coordinates are on the same line. So as I give different values of t to these three equations, I get different points of the line. So now we know that when we have a parametric equation that is x is like an x0 plus an a times t, and y is y0 plus b times t, and z is z0 plus c times t, that the vector consisting of these three coefficients of t, a, b, and c, this vector is parallel to the line. Which line? The line that is described by this parametric equation, this line. Let me give an example. Let x equals 5 minus 2t, y is minus 4 plus t, and z be 6t be the parametric equation of a line. Now, determine which of these vectors, which of the following vectors is parallel to the line. So I give 4 vectors, A, B, C, and D. One vector is vector 5 minus 4 and 0. One vector is minus 2, 1, 6. One vector is negative 5, 4, and 0. And last answer is minus 2, 1, and 0. So I look at the coefficients of t in the 3 equations that give x, and y, and z in terms of t. So in the first equation, that coefficient is minus 2. In the second equation, it is 1. So that coefficient in the second equation is 1. So here, in fact, that coefficient is 1. In the third one is 6. By the way, in the third one, obviously, this is going to be 0 plus 60, but we didn't need to write down 0. So the vector consisting of minus 2, 1, 6, or B is the correct answer. This is the vector that gives us the direction of this line. Another example. Suppose I have 2 points, and I want to find the equation, both the vector equation and parametric equation of the line connecting these 2 points, but with one condition. So let me lay out the example. So let's 2, 1, 3, and 5, 0, 4 be 2 points of a line. So find the equation of the line with this condition that where t equals 0 corresponds to the first point. So when t is 0, I should get the first point. By the first point is 2, 1, 3. So we have 2 points. The first point is 2, 1, 3. The second point is 5, 0, 4. Again, I make it in 2 parts. Part 1, I want the vector equation. And part 2, I want the parametric equation. Again, you may pause this and try on your own before you see the solution. So first of all, I find out the vector in the direction from the first point to the second point. We know how to find that, so that vector v that I find is connecting this point to the other point. We know from the first week how we can find out that vector. The first coordinate minus the first coordinate, 5 minus 2 is 3, 0 minus 1, negative 1, 4 minus 3, 1. So I subtracted 2 from 5, 1 from 0, and 3 from 4. So this gives me the direction vector. And I want t equals 0 correspond to the first point. So when I want to write the equation of the line x, y, z, the given vector or the given point will be what 2, 1, 3 will be used. 2, 1, 3 plus t times the v that we just obtained, 3 minus 1 and 1. So now this is the vector equation of the line, which connects these 2 points. And when t is 0, obviously, the first point is given. You can try this when t is 0 in this equation. The second term disappears, only we have the first term 2, 1, 3. The vector 2, 1, 3, which corresponds to the point 2, 1, 3. So once we have the vector equation, the parametric equation is quite simple because the first coordinate is 2 plus t times 3. So x is 2 plus 3t. Y is 1 plus t times minus 1. So y is 1 minus t. And z is the third coordinate, 3 plus 1t plus t. So this is the parametric equation of the line. In both equations, when I give different values of real numbers to t, I will get different points that all of them lie on the same line. And that's the line that this question was about. So now let me go back to this slide that when the parametric equation is given in this way, I know that this vector ABC tells me the direction. Now, if I have 2 lines given in the parametric form, I can determine whether or not they are parallel. So let me give an example here. Let x equals 2 plus 3t, y equals 4t, and z equals 1 plus t. And the other line, x equals 5 minus 6t, y equals 1 minus 8t, and z equals minus 2t, be 2 lines. So each of them is given in the parametric form. Now the question is, are these two lines parallel? As you might remember, in one of the previous discussions that we had, two vectors are parallel if one of them is number times the other vector. So if one of them is scalar multiplication of a number with the other vector. So for the first line, the direction vector, or the vector that gives us the direction, let me show it by V1, consists of the coefficients of t, 3, 4, and 1. 3, 4, and 1 here, that's coefficient of t. In the other one, the coefficient, so V2, the direction vector of the other one, V2, consists of -6, -8, and -2. Now the question gets reduced down to this question: are these two vectors parallel? Is it a real number? When I multiply by one of them, I get the other one. Yes, we can, because like I can write the second vector, -6, -8, -2, as -2, a scalar multiplication by the other vector, 3, 4, 1. So since I'm able to write one of the vectors as a not real number, a scalar multiplication by the other vector, the answer is yes. So therefore, the answer is yes, and these two lines are parallel because their direction vectors are parallel.